Let's talk about limits. Limits are an important concept to grasp, and they really provide a foundation for a lot of the concepts we're going to look at going forward. So, what is this limit here? What is it saying? Well, the way I would read this is limit as x approaches to of x squared. So x squared is an equation, right? It's a function, y equals x squared, and I've sketched out what it looks like. We all know it's just the parent function of a quadratic. Now, what do I mean as x approaches 2? Well, you can think of it as we have a point here on our graph that has an x value of 2. And you can approach that point either from the left-hand side or you can approach it from the right-hand side. And so you can actually kind of imagine you are a point on this graph and you're getting closer and closer to an x value of 2 from one direction or from the other direction. It doesn't really matter. As you're approaching that point from both directions, your y value is also approaching a certain value. If you move towards that point from the left, your y value is getting bigger and bigger until it reaches this y value. If you approach the point from the right, your y value is getting smaller and smaller until you reach that y value. The question is, what is that y value? Well, to figure it out, you can simply plug the number 2 into this x. You would get 2 squared, which is 4. So this point here has the coordinates 2, 4. So when we exist as a point on this graph, as the x value approaches a value of 2, the y value will approach a value of 4. Hopefully that makes sense, and you're able to visualize it as you're moving along the graph. This is the first thing you want to try when you evaluate a limit. You don't always want to sketch it out, but the first thing you can always try is substituting that number into the equation for x. That's the first thing I would try. Now, let's look at another example. Let's say we have the limit as x approaches infinity of x squared. Well, what does this mean? X is approaching infinity. Well, an x value of infinity would be very, very far to the right. It essentially means as x goes to the right forever. So this continues, it keeps going to the right and it keeps going up. And that kind of answers my question, right? What happens to the value of y as the value of x gets bigger and bigger and bigger? Well, this just continues in this direction forever. So we can say that as the value of x goes towards infinity, the value of y also goes towards infinity. Your answer is infinity. And if you were to plug infinity into your equation here, infinity squared is equal to infinity, right? Infinity times itself is infinity. So that's another way you could figure this out. But logically, you want to make sense of this, right? You want to understand that as x is getting bigger and bigger and bigger, right? X is going to infinity. You're going very far to the right, that your y values are increasing very, very high. They're also going towards infinity. So in summary, I could say as x goes to infinity, that y also goes towards infinity. Now, you can also make the observation that as we go very far to the left, right, as x approaches negative infinity, I would say, the limit as x approaches negative infinity of x squared, that just means we're going very far to the left, your y values are also increasing, right? They're also going up as we go far to the left. So the limit as x approaches negative infinity of x squared should also equal positive infinity. And you can figure that out by substituting negative infinity into your equation here, negative infinity squared. Anything negative times itself or anything negative squared is going to be a positive. So negative infinity times negative infinity gives you positive infinity. So mathematically here, it checks out with what we're observing in the graph. So hopefully you're getting a sense now of what a limit represents, right? We're just saying what's happening to y as this happens to x. That's all we're doing. If I look at another function here, y equals 1 over x squared, we can be asked the question, what's the limit as x approaches 0 of 1 over x squared? Well, visually, you can take a look at this, and you'll see that as we move towards 0 from the right-hand side, the y value is getting bigger and bigger. It's going up and up and up. As we approach 0 from the left-hand side, so you're getting an x value that's closer and closer to 0, the y value is also going up. So it doesn't matter if you're coming from this direction or if you're coming from this direction. In both cases, the y value is increasing. So I would say that the answer here is infinity. It's actually positive infinity to be specific because we're going up. Now, a few things to note here. If you try to substitute in your 0, what you're going to get is 1 over 0 squared, which is 1 over 0, which is undefined, right? We don't want undefined as an answer. But you can think of it in another way. You can say as the denominator of this fraction gets smaller and smaller and smaller, the value of the entire fraction as a whole gets closer to positive infinity, because a number divided by an infinitely small number will give you a very, very large number. Imagine, for example, that instead of 0 on the bottom, you had a number approaching 0, like 0.00001. Well, if you did 1 divided by that, you would get a very big number. As this number on the bottom gets smaller, the overall number gets bigger and bigger. In other words, it's approaching infinity. So mathematically, this is a way that you can logically say the limit approaches positive infinity. You can also look at it graphically and say, oh, as my x value gets close to 0 from the left, and as my x value gets close to 0 from the right, my y value is increasing. So y is increasing, that means it's approaching infinity. Another important point here, in order for us to say that the limit as x approaches 0 is infinity, that has to be true from the left and the right hand side. Both have to be true. And you can show this using limits. You can say the limit as x approaches 0 from the right, and you'll see a little plus here. It's a little superscript. It kind of looks like an exponent. This means that we're approaching 0 from the right. So the limit as x approaches 0 from the right of 1 over x squared, that is positive infinity. We know that because we can approach 0 from the right-hand side and we see we're going up. And we can also do the limit as x approaches 0 from the left. And you put a little negative there of 1 over x squared, and that will also equal positive infinity. We know that because we can approach it from the left-hand side and it goes up. So both of these things need to be true. This needs to be true and this needs to be true. They need to give you the exact same answer in order for us to conclude that the limit as x approaches 0 in general, not just from the right or from the left, but just in general, of 1 over x squared equals positive infinity. These both need to be true in order for this to be true. That's very important. Hopefully that makes sense. Okay, let's do another example. In this case, we have the same function that we're dealing with, 1 over x squared, but now x is not approaching 0. We actually have two limits here, one where x approaches negative infinity and one where x approaches infinity. Well, what does this first one mean? What does x approaching negative infinity mean? It means that your x values are getting smaller and smaller, or they're going very far to the left, right? So if you want to start here, for example, your x values are approaching negative infinity. You're moving farther and farther and farther to the left forever. Well, that means that your y value would be approaching what? Well, it's approaching 0, right? Because what's the height of a point here? It's just barely above your x-axis, right? You have a horizontal asymptote here. I know we've talked about asymptotes in the past. If you're just above the asymptote, and in fact you're getting lower and lower, you're approaching the asymptote, then we can say that the limit in this case will equal 0. Now what's the limit as x approaches positive infinity? So if you have a point here and it moves further and further to the right forever, right? X is approaching infinity. You're going very far to the right. Well, that's also approaching 0, right? Your x value starts, or your y value, sorry, starts up here, and it gets lower and lower and lower, and it continues to get closer and closer to that asymptote forever. It approaches a value of 0. So you can actually approach numbers. You can also approach infinities like we did in this case. Let's look at another example. We have a similar function here, except instead of 1 over x squared, it's 1 over x, and of course that gives you a slightly different looking graph. If we decide to figure out what the limit is as x approaches 0, okay, so let's start with x approaching 0 from the right, and I'll actually write it out this time. What's the limit as x approaches 0 from the right-hand side of 1 over x? Well, as we get an x value closer and closer to 0, I'm approaching 0 from the right-hand side. The y value is increasing. The y value is getting very close to positive infinity. It goes on and up forever. Well, what happens when we do the limit as x approaches 0 from the left of 1 of x? Well, if you start here and you start approaching an x value of 0 from the left, you realize you go down and down and down, you go lower and lower, that's negative infinity, right? These are different answers. As you approach an x value of 0 from the different directions, your answers end up going in different directions, right? They're not the same. So because of that, we have to say that the limit does not exist. And you'll often see me use DNE for does not exist. So in this case, the limit does not exist. Let's go to another example. Let's say we're finding the limit as x approaches 2 of x squared minus 4 over x minus 2. In this case, I haven't provided you with the graph, and we don't necessarily need the graph to figure this out. We're going to do it purely mathematically. Let's figure this out. So let's try to start by plugging in the number 2. If we try to plug in the number 2, you get 2 squared minus 4 over 2 minus 2. 2 squared is 4. 4 minus 4 is 0. 2 minus 2 is 0. Uh-oh, this is a problem. It's undefined, right? We can't divide by 0. This is actually a case of what we would call the indeterminate form. Let me write that out for us. The indeterminate form. And the indeterminate form is something you get when you try to plug in your limit right away. And it can be something like 0 over 0. It could also be something like infinity over infinity, or 0 times infinity is another case. Infinity to the exponent 0, 0 to the 0, 1 to the exponent infinity, infinity minus infinity, anything like this where you really don't know what to make of your answer, right? Like infinity over infinity, does that equal infinity? Does it equal 1? Like, what does that mean? 0 to the 0, what does that mean? Because we know 0 to the exponent anything is 0, but I also know anything to the exponent 0 is 1. So what does that mean, right? So all these answers you could get when you try to plug in your answer right away. And if any of these things happen, that means we have the indeterminate form and we have to try something else. So how do I try something else in this case? Well, one thing you can try to do is factor. Factoring is always a good idea. So the limit as x approaches 2, let's change this so that it's factored. The bottom is already factored. We can't do anything with that denominator, but the numerator is a difference of squares. We can factor that by saying x plus 2 multiplied by x minus 2. If you forgot about factoring, go look at this video. Now, once we've factored it, you're going to clearly see that there is a term we can cancel out, x minus 2 and x minus 2, because anything divided by itself is 1, meaning we're left with the limit as x approaches 2 of x plus 2. Well, now you can plug in that number. 2 plus 2, right? We're plugging in 2 for x. 2 plus 2 is equal to 4. Therefore, our limit as x approaches 2 is equal to 4. Now, if you tried to plug the 2 into the original, we don't get the answer 4. We get this indeterminate form. So why do we get an answer once we cancel things out? Well, the reason is because the point 2, 4, right, the x value that we had and the y value we found, this is not actually a point on the original function. Rather, this is a point that our graph approaches. What do I mean by that? Well, if I do a very crude sketch here of what we have, our graph actually looks something like this. It's a graph that has a hole or a discontinuity, right? I'll use the word hole to describe this, but another term you'll hear is removable discontinuity. And what that means is that at the point 2, 4, there's a point missing in our line. I know that it's a line like this because once we canceled out those terms, we were left with x plus 2, and y equals x plus 2 is just a straight line that has a y-intercept at 2, right? So it's a line that looks like this. Y equals x plus 2 would be this line, except there's a hole there. Because there's a hole, this is not actually an accurate equation to represent this line. Now you can clearly see that as you approach 2 from the left-hand side, or as you approach 2 from the right-hand side, you're approaching a y value of 4. But that point doesn't really exist, right? That point is missing from our line. So even though as x approaches 2, y is approaching 4, and that's true from both directions, if you just plug in 2, you're not going to get 4 because that point is missing from the graph. So that's the scenario that's actually being painted by this equation, right? x squared minus 4 over x minus 2 is this graph. When you take the limit as x approaches 2, you're finding the location of that hole. You're finding the y value of a theoretical point that could be there but is missing. And again, that hole can also be referred to as a removable discontinuity. So if you ever get the indeterminate form, something funky like this, try and see if you can factor and then cancel anything out. And when that happens, try to evaluate your limit at that point by plugging in the value of x. Let's look at another example here. Let's say we have the limit as n approaches infinity of 3n squared minus 2n plus 1 all over 4n squared plus 1. Now, if you try to plug in infinity here, it's going to be very confusing what we're dealing with. There's going to be a lot of infinity terms, and we're not really going to be sure how to simplify things. So what can we do? Well, this is often the case when we have a polynomial over a polynomial. What you can do is actually divide every one of these terms by the variable you have raised to the largest exponent that you have. What I mean by that is if you look at all the terms with a variable, they all have an n. The biggest exponent we have on n is a 2. What that means is I would want to divide every term by n squared. Divide everything by n squared. And you're allowed to do that, right? If you change the numerator, as long as you change the denominator in the same way, you can do that. If I divide the entire numerator by n squared, you just have to divide the entire denominator by n squared. Once you've done this, we can simplify our limit. 3n squared over n squared is simply equal to 3. 2n squared over n squared is equal to 2 over n. 1 over n squared is 1 over n squared. That doesn't change. On the bottom, 4n squared over n squared is 4, and 1 over n squared is the same thing, 1 over n squared. Now at this point, let's think about what would happen if I plugged infinity in for n. So this becomes infinity, this becomes infinity squared, which is infinity. This also becomes infinity squared, which is infinity. If I do that, what happens? Well, I have 3 minus, what's 2 over infinity? Well, any number over infinity is approaching a value of 0, right? An infinitely small number relative to an infinitely big number is something that overall will approach a value of 0. Same is true for this one. We have a value of 0. On the bottom, you have 4 plus a value of 0. And so altogether, I can say, well, these aren't doing anything. I just have 3 over 4. So the limit as n approaches infinity is a value of 3 over 4. And you might recall when we did our curve sketching unit last year that when we talked about horizontal asymptotes, if you look at the polynomial on top and bottom, if the variable you have is raised to the same exponent on the top and bottom, that if you look at those coefficients, you can use those coefficients to figure out where the horizontal asymptote is. The horizontal asymptote in this case would be at a value of y equals 3 over 4. This is the reason for that. This is the proof. You take the limit of this equation and you end up getting 3 over 4. So as the graph goes very far to the right and very far to the left, in this case we're only going very far to the right because we're saying infinity is positive, right? So as you travel very far to the right on this graph, you're going to be approaching a y value of 3/4 because that's where the horizontal asymptote is. If I was going to sketch this out, and you could sketch this out on Desmos if you like, so this is your n and your y. You could have used x, but this example used n instead of x. There's a horizontal asymptote here at a y value of 3/4 or 0.75. Now this particular graph is kind of a funky one. It kind of goes up like this and then it comes down. It actually crosses the horizontal asymptote and then comes back up. It doesn't actually touch the asymptote, of course, over here. It just approaches it. It only crosses it here. But you can see as you travel very far to the right, as x approaches infinity, or I should say n, as n approaches infinity, as you go very far to the right, your y value is approaching a value of 3/4. So that's what's going on here. So if you have a polynomial over a polynomial like this, there's a good bet, especially if you're approaching infinity, that you can simply divide all your terms by that x to the biggest exponent, And by doing so, you'll have a bunch of terms turn into 0 once you plug in infinity, and you'll be left with those first two coefficients. So you can kind of use that as a shortcut, but go through the process, show your work, and you should get that as an answer. Okay, let's do another example. Let's say I'm taking the limit as x approaches 9 of x minus 9 over the square root of x minus 3. This is one of the trickier ones to do because if you plug in the value of 9, square root of 9 is equal to 3, right? And if you have 9 minus 9 over 3 minus 3, you're going to get 0 over 0, and that's no good, right? We don't want the indeterminate form. So what can we do instead? Well, this is a very specific procedure. This is called multiplying by the conjugate. What is the conjugate? The conjugate is the opposite of this thing. So where you see square root of x minus 3, over here you're going to put the square root of x plus 3. And if you multiply by a fraction, the top and bottom have to be the same because that's like multiplying by 1, right? We can't actually change this equation, but we are allowed to multiply it by 1. The reason you want to use the conjugate here is because once I multiply these things together, this times this, the plus and the minus are going to cause some canceling to happen, and this is actually going to clean up very nicely for us. And again, this is referred to as the conjugate. So let's actually do the math. The limit as x approaches 9, the numerators, I'm not really going to bother distributing or multiplying those out or expanding them. I'm just going to write x minus 9 multiplied by the square root of x plus 3. I'm going to leave that alone. But the bottom, the denominator, is what I'm interested in. Because if I expand the bottom, if you think of this as two binomials, which is what it is, and I multiply them together, square root of x times square root of x is x. Square root of x times 3 is 3 square root x. Negative 3 times square root x is minus 3 root x. And minus 3 times 3 is minus 9. This is what I was talking about. Your 3 root x minus 3 root x will cancel one another out. And if you can't see it now, I'll clean up the question a little bit to help you. Limit as x approaches 9, x minus 9 root x plus 3 divided by what's left on the bottom, just x minus 9. If you want to put that in a bracket, you can. You can clearly see that x minus 9 on the top and bottom will cancel one another out, and you're left with the square root of x plus 3. I can now try to plug in my 9. Square root of 9 plus 3, that's equal to 3 plus 3, which is equal to 6. So 6 is your final answer. The limit as x approaches a value of 9 is 6. So as x gets close to 9, y is going to get close to 6. So that point, 9, 6, right, that coordinate, 9, 6, that's a point that you're approaching when you're dealing with this graph, but that point doesn't actually exist on the graph. And I know that because when you plug in a value of 9, you get that indeterminate form, right? You get 0 over 0. So because of that, that point doesn't exist, but it is a point that we are approaching on the graph. So finally, just to recap, whenever you're dealing with a limit, there's a few things you can try. The first thing I always try is plugging in the number, just like we did in question number 1. That's why I have a little 1 written here. The second thing I always try, if that doesn't work out, if I get an indeterminate form, if I'm dividing by 0, something weird like that, the next thing I try is I try to factor and then cancel, just like we did in question number 6. Try to factor what you have on the top and bottom, and perhaps something will cancel out. Once it cancels out, then try to plug in your value for x and see if you get a reasonable answer. Another thing you can try after that, use the conjugate. Again, if you're using a conjugate, it's usually a question like number 8. It usually will look very similar actually to question number 8, where you have the root of a number plus or minus another number. That's the most common scenario that I see it pop up, but there could be different scenarios where it's useful, so try that next. After that, if that hasn't worked, try to divide everything by x to the exponent, whatever the largest exponent is. This is most common like in question 7, where you have a polynomial over a polynomial, and your limit is x approaching infinity, or a negative infinity, it could be. So in those situations, that's what you're going to want to try. And then finally, if you really don't know what to do, nothing else worked, or maybe you haven't tried everything else and you're drawing a blank and you don't know what to do, you can always try to approximate from each side like we did in question 3. And you can do that by visualizing it with the graph itself. If you don't have the graph itself, you can try to plug in numbers that are close to what you're approaching. So for example, if the limit of whatever the function is has x approaching 0, well, try to plug in values of x like 0.1, then plug in 0.01, 0.001. This is us approaching an x value of 0 from the right. You can also approach 0 from the left by plugging in the negatives, negative 0.1, negative 0.01, negative 0.001. This is us approaching an x value of 0 from the left. You can also say, well, what if x is approaching infinity? Well, if x approaches infinity, then you can plug in bigger and bigger numbers, 1,000, 1,000,000, 10 million. Plug in bigger and bigger numbers and see what your y value is approaching. That is another valid solution to trying to figure out what the limit is. So try to do that if you can. If you get stuck, if there's nothing else that's working for you, try to do that as a last resort. Hopefully this clears up limits, what they are, and how to solve them. Keep practicing and try to keep these rules in mind, right? Try to go through each of these rules with every question and try to identify, when you get the question at the start, what rule you think is going to be the most useful.